Welcome to Statistics. I'm Dr. Jeff Groh. Statistics is an important subject, and you'll find that if you let it, it can change your understanding of the whole world. As with every subject, we have to begin with a discussion of the words that are going to form the basis for our discussion. So, first, a definition. A census is a collection of data from every member of a population. So a census requires that the data be collected from everyone. A census is very big and expensive and difficult to do. And so we often use instead a sample. So for us, a sample is a collection of data from some subset of the population. You'll often see various polls published. Those polls will often have somewhere between 1,000 and 3,000 individuals being sampled. They're not asking something from the entire population, but only from some sample. And since that is such a small proportion of the population, you can suspect that there may be sources of bias that could easily enter into the sampling process. An example is a voluntary response. A voluntary response sample is one where the respondents decide whether or not to participate in the sample. So for example, you may have an internet poll where people decide whether or not they want to click yes or no or whatever the options are on a particular poll. Another example might be call-in polls, where the individual has to make the choice to dial the number and call in order to respond to the poll. Not that someone calls them, but that they have to call and give their response. Another example might be a mail-in poll. You may be asked to mail in some choice or some response. These are all examples of excellent ways to construct very biased polls that won't tell you much about the population. In the statistical process, there are three main steps. You prepare for a survey or poll. 2, You analyze. And 3, you make your conclusions. So when you prepare to conduct some kind of survey or poll, you first have to decide for the content. Then you need to decide the data source and the sampling method. How are you going to choose those who participate in providing those answers? In analyzing the data, you might graph the results to help you gain a broader understanding of what the data is telling you. You may find outliers, data values that are so far out of the norm that maybe they should be excluded. You may find missing data. And then you may apply various statistical methods. In analyzing the data. As far as conclusions are concerned, you may need to consider the statistical or the practical significance of the data that you have found and of the interpretations that you have made of that data. Let's consider some of the data pitfalls. You may have too small a sample size to be representative of the population that you're trying to estimate some parameter for. So for example, if I have some issue and I want to know how people feel about this issue generally, say nationally, and I talk to 3 of my best friends, 3 is pretty small, and it's certainly not a random sample by any means. So it may not represent the opinion of the entire population. Even if I try to randomize the entire population and I choose 25 people for my sample, that sample size may be too small to really get an idea of how the nation as a whole feels or believes about a particular question. Also, we have to be careful about our conclusions. We should not infer too much. The data is the data, and it doesn't tell us about more than just what is in the data. Also, we should be careful that correlation does not imply causation. Suppose, for instance, that I have a fantastic sample size of, say, 10,000 individuals, and I am able to infer from this that there's a very high correlation between shoe size and IQ among adult males. Well, does that really mean that having a small shoe size implies you'll have low IQ? I think not. These may be unrelated variables, but just happened to have a high correlation. Who knows? There could be any number of reasons for that. If you collect all the data yourself, you may be introducing unconscious biases just by the way you say that you ask a question, the inflection of your voice, etc. The force of your personality may cause people to respond one way when to another person they would have responded in a different way. So having all the data collected by yourself or just by one person, that could introduce biases to the data. Survey questions may be loaded. We could ask people questions that imply that if they answer one way, then they're racist. Well, nobody wants to be called racist or be accused of it, and so they'll answer the question in the way that you would, say, prefer that they would answer it. As another example, often political campaigns will have what they call push polls. They'll have a poll that they conduct where they contact individuals within a community, and they try to word questions in such a way that they support a particular candidate. So when they publish these results, they can claim to have evidence of widespread support for that candidate in the community, when in reality all they've done is force people to answer questions a particular way by wording the questions in some awkward fashion. Another pitfall is the non-response rate. It's not uncommon to have very small numbers actually respond to a poll. You might even have only 20 or 30% of those who you approach decide to participate in the poll, and so your answers may not be reflective of the population in general. In fact, sometimes certain political groups may decide that it's not in their interest to respond to any poll, so they just refuse to take part. And when that happens, you'll have biases entered into your results. You may have missing data. Sometimes people are just hard to find. If you're trying to find out about migrant workers, then maybe that data might be missing because you just find it difficult to find them. Another example may be colleges and universities who, try as they might, sometimes find it difficult to collect all of the data that they need. Some professors may fail to submit a certain form, and so you may have data that's just not there. Another problem is that numbers may be given too precisely. And this is particularly a problem when you're reporting your results. The numbers that you report may not reflect the accuracy of the survey. Also, we have to be careful about percentages. One example may be average income. Average income is pulled way off from the middle of the income group by individuals who happen to have a very large income. And so the average can be pulled way off. The distribution of incomes might look something like this, where you have a little bump here of people with very high incomes. So the average will end up being over here because of the high bump, whereas the median income may be over here, closer to the middle of the group of incomes. A parameter is some numerical measurement describing some characteristic of a population. So parameters apply to describing a population, which is very different from our next term. A statistic is some numerical measure describing some characteristic of a sample. You can see the difference between a parameter and a statistic. Parameters apply to a population. Statistics apply to a sample. So pay attention to that alliteration. We talk about a population parameter and a sample statistic. That helps you to remember which term applies in which case. As an example, there are both population means and sample means. These means are some kind of a measurement for the middle of the data. But if you're calculating the mean for the entire population, that would be a parameter that applies to the population. So the population mean is an example of a parameter for that population. Alternatively, if we just take a sample of individuals from the population and find the mean of some characteristic from that, that mean would be a sample statistic. So taking it from a sample means it's a statistic. Taking it from the population means it's a parameter. There are various ways of classifying data, so I want to give you data types. First, there is quantitative data, or numerical data. Quantitative data consists of numbers. Alternatively, there's qualitative data or categorical data. These might be names or labels. So for example, blue eyes versus brown eyes. We can call those names. Those are qualitative characteristics. Whereas if I count the, say, the height of individuals, that would be quantitative and numerical. An example where labels could be numbers might be, for instance, numbers on player jerseys in a sports team. Those numbers don't really have any kind of order to them. The number 82 is not greater than the number 7. The player 7 may be the best player on the team. We don't know. There may be no way to quantify that. Those labels then, even if they are numbers, may be only representative of some kind of a name, a qualitative nature of the particular data, and be qualitative in nature. So these qualitative data could consist of numbers if those numbers are being used as a label and not in the usual numeric way. Alternatively, data could be classified as nominal, ordinal, interval, and ratio. So nominal data is just names and labels. Ordinal data has an order to it. So 1 is less than 2. But it doesn't have to be numerical necessarily. It could be excellent versus average. Or it could be some scale about pleasure or pain. Highly pleasurable, somewhat pleasurable, quite painful. Who knows what the ordinal kind of data may consist of. There are many different possible examples. As long as there is an order to the data, whether it's numeric or not, then it is ordinal data. Nominal data cannot be placed in an order, and that's what makes it different. With ordinal data, the differences are meaningless. Which is the difference between interval data and ordinal data. As an example of interval data, where differences can be found and are meaningful, I'll give you the example of temperature in degrees Fahrenheit. Degrees Fahrenheit, the differences are meaningful. 100 degrees is very different from 32 degrees Fahrenheit. So the intervals between those, how big that interval is quite meaningful to you. That difference is meaningful. Clearly, this interval data does possess an order, but the distinction is data is ordinal if those differences either are undefined or the differences are meaningless. One thing about degrees Fahrenheit is that the number 0 degrees Fahrenheit is kind of chosen arbitrarily. Where that 0 is doesn't make a lot of difference. It would make much more difference if we used degrees Kelvin. In the Kelvin temperature scale, 0 is absolute 0. And so there, different ratios of those temperatures might make a lot more difference, have a lot more meaning than ratios of degrees Fahrenheit. So a classic characteristic of interval data is that there is no natural 0. Or it could have a 0, but it's not natural, it's kind of randomly chosen. So in ratio data, it's also interval data, but you have a natural 0. You might take, for example, heights. There's a natural 0 height versus all other positive heights. The gap between the heights makes a difference, but there is a natural 0 present in ratio data. So degrees Kelvin, the Kelvin temperature scale has a natural 0, absolute 0. Duration is another example where there's an absolute 0. Something lasts 0 seconds versus something that lasts 3 years. So yes, duration has intervals, and there's a natural notion of difference between them, but there's also a natural zero, and that makes it ratio data. There is a classification for quantitative data. For example, there is continuous data, and there is discrete data. In continuous data, the data has values in an interval of real numbers. So for example, heights. You can take any height, you can have any height in between some interval. But discrete data is taken from little disjointed pieces of the number line. As an example of discrete data, you might look at the number of chairs in a classroom. The number of chairs doesn't usually take on a fractional value. Let's assume all of the chairs in these classrooms are in good working order, in which case the numbers of chairs in a classroom will be some natural number. 1, 2, could be a whole number, could be 0. You could have rooms with no chairs. Or it could be 1, 2, 3, 4, and so on. But it usually is not something like the square root of 2 number of chairs, 1.414. So the discrete data doesn't take values in an interval, it takes these discrete separated values. Data inappropriately collected is useless. Yes, bad data gives you bad conclusions. And so you just have to throw the data away and start over if it was collected badly. In an observational study, we observe and take measurements but we do not attempt to modify the subjects. You can take data from the subjects, but you don't modify them. So for example, we could take each subject's height, but we're not trying to change their height in any particular way. That would be an observational study. In an experiment, on the other hand, we apply some treatment. And then observe the effects on the subjects. The subjects are called experimental units. So in this case, We may apply some new medication to a group of individuals and then observe the effects of that medication on those individuals in treating some particular, say, disease, or in trying to improve their health. So experiments are very different from observational studies. In the experiment, you're actually trying to affect the experimental units, to put it euphemistically, these subjects. As a special note, in experiments, we try to control variables to avoid unexpected complications. If I were doing an experiment affecting pressure and volume that didn't pay attention to the temperature, then some temperatures I might have a particular volume and a particular pressure, and in another case I might have the same volume and a different pressure, which results from maybe a different temperature. So because I wasn't checking the temperature carefully, the pressure might not be well regulated as a consequence. As another example, my daughter once had a science experiment for her science fair, and the idea was that plants growing in a carbon dioxide atmosphere will grow more vigorously. So we thought that we could establish an atmosphere of carbon dioxide using dry ice, since it's just a solidified form of carbon dioxide. So we obtained some dry ice from a local dry ice seller, and we placed that dry ice in with these plants and then closed these plants in, giving them an enclosed environment with an atmosphere that consisted of almost pure carbon dioxide versus other plants which grew in air. Well, after so many weeks, we checked the plants and see how they were doing and found out that those growing in the carbon dioxide atmosphere had all died, whereas those growing in air had done fine. Come to find out, the carbon dioxide that we were buying from this particular source was contaminated with ammonia, which was their refrigerant. Their refrigerant was leaking into the carbon dioxide. And so these plants received a healthy dose of ammonia that killed them. So the experiment failed in that sense because of this confounding factor. We didn't control for the unexpected presence of ammonia in our dry ice. Surveys are observational studies. Cancer drug trials are experiments. Of high importance in this course is the notion of a simple random sample. A simple random sample of size n could be some number like 30 or 30,000. A simple random sample of size n is chosen so that every other sample of size n has an equal chance of being chosen. So you look at all possible samples of size n, you give them an equal chance of being selected, and then you choose one. That gives you a simple random sample. A mechanism that you might use for choosing which of these different samples you are going to choose might be through a random number generator or through some kind of a lotto ball selection scheme. Anything that introduces that sense of randomness and there being an equitable choice for all of these different samples. That gives you a simple random sample. I should mention that many of the statistical techniques that we will use in this course specifically require that you use a simple random sample. That isn't the only possible way of choosing a sample, however. Other sampling methods there is systematic sampling. An example might be, suppose you have a machine and it's a really bad machine. Let's suppose it produces a bad unit, and then a good unit. A bad unit, and then a good unit. So every third one is good, but 2 out of 3 are still bad. And let's suppose your sampling method chooses every third one to look at. As far as you are concerned, it looks like from your sampling method that all of the units are good because you're choosing every third one, only those that end up being good with this particular machine. And so you're producing a systematic error as a consequence. As an example of convenience sampling, suppose that you want to know the opinion of a student population on some matter, and so you talk to your friends. Your friends may be convenient sources of information, but they'll also introduce a lot of bias into your sample. So in convenience sampling, you use data that is easy to get, easy to acquire. In stratified sampling, you divide a population into groups, then you sample from the groups. So, for example, you might divide the population into those who live in certain zip codes, and then sample from the different zip codes. That would be a stratified sample. In cluster sampling, you divide the population into groups, then you take all of the elements of a particular subgroup as your sample. In multi-stage sampling, use 2 or more methods at 2 or more stages. As an example, You might say select a particular county in a state and then take a random sample from that county. Or you might take a sample, you might choose a different number of counties, ignoring other counties, and then find simple random samples from each of those counties that you've chosen. That would be a multi-stage sampling. There's more that we can say about observational studies. If it occurred in a past period of time, it is a retrospective study. If it occurred at one point in time, it's a cross-sectional study. Those looking forward in time are prospective in nature. Prospective studies are sometimes called longitudinal, in which we follow groups sharing some common factor. For example, we might follow over the course of 20 years groups of children who took the rubella vaccine, follow them into adulthood, and see their outcomes. Such a study that takes place over a long period of time, a period of years, is a longitudinal study, whereas if you just look at what happens at a particular point in time, that's a cross-sectional study. There are important aspects of experimental design that you need to be aware of. One important aspect is randomization, where individuals are chosen to be part of particular groups through a random process. We often have an experimental group and a control group. If we're experimenting with a particular drug, we often give members of the control group a placebo, maybe a pill made out of sugar, which we don't expect to have any particular impact on the experiment being performed. It's important that members be chosen at random to be parts of these groups. It's quite possible that some individual may sincerely want to try some new drug, and they're wanting that drug to be applied to them and to cure whatever disease they may have, may affect the responses that they give to their health practitioner. And so we talk about blinding. In a double-blind process, the person giving the treatment to each person, whether they're in the experimental group or the control group, that person doesn't know what group those individuals are in. He or she doesn't know what drug or placebo is being given to the individual. And it being a double-blind study, the experimental group and control group people receiving the treatment or the placebo, don't know which they are being given. So you can imagine the complications in forming such a study, where the experimenter who is giving the drug, let's say it's a drug for cancer, He doesn't know whether he's giving the drug or giving a placebo. You have to have the drugs labeled in some kind of a vial that doesn't have the drug per se on it, but the drug may be identified by some barcode that neither the person receiving the drug nor the physician administering the drug can identify. So in a double-blind study, the giver and the receiver don't know which group the receiver of the experimental treatment is in the experimental group or in the control group. So there's the double-blind nature of certain experiments. This is important because there is something called a placebo effect. People being given something will often feel an effect, even if it's just a sugar pill, and it should have no effect. They want it to have an effect. They believe that it should have an effect, and so they try to make themselves believe that the drug is having an effect, when in fact it is not. It's possible that that very belief that they're taking something that helps them can relieve their mental stress and somehow allow them to find improvement in their condition. Besides randomization, you must have replication. There are a couple aspects of this. First of all, you should be able to repeat this with more than one individual. So, a large sample size may be necessary, but you must also be able to repeat the experiments with different experimental groups. Even better if they're coming from different experimental laboratories. Those working under one roof might have the same biases through some common source of funding. It's better if there are completely unrelated and unbiased groups of researchers who approach the experiment and try it themselves. And if the new group cannot replicate the results from the old group, then that seriously calls into question the results. There may have been some additional bias introduced by the original group. Confounding occurs in an experiment when investigators cannot distinguish among the effects of different factors. As an example, suppose you have an educational experiment where the experimental group consists of fourth graders and the control group consists of third graders. In this case, just the fact that there's a grade difference between the different subjects means there could be a big difference in the outcome of the experiment. Was the effect on the fourth graders caused just by the fact that they were in fourth grade and not by the experimental treatment being applied? In a completely randomized experimental design, we assign subjects to different treatment groups by a process of random selection. We don't allow bias to enter by individuals wanting to be part of the experimental group and not part of the control group. It's important to have a control group. You cannot really tell if some treatment has the desired effect if you don't have that control group to see what the effect of doing nothing is. In a randomized block design, group subjects by similar characteristics and then choose randomly subjects for the experimental or control groups from each of these subgroups. An example might be separating your subjects into male and female, and then randomly choosing treatment or placebo within each of the groups, male and female. That way, you can see that there won't be some confounding factor. There's something called the matched pair design. Here we compare two treatment groups based on matched pairs. It could be before and after. Suppose we're trying to understand the effects of some skin whitening product to remove blotchy patches of skin on the back of one's hand. You can take an example from before, apply the treatment, and then compare after. Another example might be checking the effect of some treatment on twins. It's phenomenal how often identical twins will have similar preferences, even if separated at birth. Sometimes they're even found to enjoy the exact same brand of cigarettes. Perhaps there's something genetic about their preferences. Applying some treatment to identical twins can give you a pretty good idea of its effect based upon differences in the pair. A rigorously controlled design helps to weed out confounding factors. Here, we assign subjects to groups having similar characteristics that may be important to the experiment. For example, suppose we're testing a new heart drug, and we have a 27-year-old heavy smoker who is also a heavy drinker and has other unfavorable characteristics that would maybe confound what it is that we're trying to study, the effects of the drug on heart health. There are certain errors that arise just because of the sampling process. You can have a random sampling error You may have chosen a random sample that just didn't represent the population. So in this case, there is a discrepancy between our random sample results and the true population result. That's fair enough. it's not always possible to avoid the introduction of errors, because after all, we are just taking some small portion of the larger population, it being impossible to perform most experiments on the entire population. There is the non-random sampling error, where the error was introduced through some non-random sampling process, like for instance a convenience sample or a voluntary sample. And yes, there are non-sampling errors. Through just the nature of being humans, we could introduce some kind of human error into the process, or even a data entry error. You might type one too many zeros on some particular data value. You might make a computational error. An error in just your calculation, an error in arithmetic. It's possible that the respondents lie. They could just tell you something that's wrong just to be persnickety about it. Or there may be groups that feel slighted and hence feel fully justified in lying to those who ask them questions, to purposefully try to throw off the result. In addition, you could have biased conclusions. Or inappropriate statistical methods.